Number 7 asks us to figure out what the resultant force is given two forces with an angle in between. So I've already taken a second to go ahead and draw the picture. So I've got a force of 80 pounds, another force 140 pounds, and I've got my resultant force, which we know is going to be in between those two, and we have an angle that's in between. So first thing I'm going to do is say, well, I know if I use this like parallelogram rule, or a little trick that we talked about, that the opposite sides are also going to be equal. So what I mean by that is that this is also going to be 140. This is also going to be 80. We know that about a parallelogram. Perfectly legal way to do this. Well, what do we have here? We have basically two triangles, one on the top and one on the bottom. Well, we know that angles in a parallelogram are supplementary if they're right next to one another. So if they're supplementary, take 180 degrees and subtract 75, I'm going to get 105 degrees for this angle at the top. That's going to be the same thing down here. But I'll just worry about this triangle at the top in order to solve the problem. So in order to figure out R, the resultant force, how large it is, we're just going to use the law of cosines. Because really what we have here is a situation of side, angle, side. And from the previous video when we had side, angle, side, we right away used the law of cosines. So anyways, I'm going to write R squared is equal to 80 squared plus 140 squared minus 2 times those values and then the cosine of the angle that both of those sides touch, which is 105 degrees. If we figure out what R squared is, we get a pretty big number, 31,797.55. Take the square root of both sides of the equation, we get R is equal to 178.32 pounds. So pause, see if you can do number 8. I've already got the diagram drawn for you. So you can do number 8 the exact same way. Okay, so let's see how you did. Again, opposite sides are going to be equal, so here's 92. Here's 65. We know that our angles that are next to one another or adjacent angles in a parallelogram are going to be supplementary. So this angle right here is 180 minus 42, which gives you an angle of 138 degrees. So I'm going to use the 65, the 138, and the 92 just like I did in the above problem. Looks very, very similar, just different numbers. So I'm going to write R squared is equal to 65 squared plus 92 squared minus 2 times both of those numbers that I just used there, 65 and 92, cosine of the degree that they both touch, 138 degrees, if you plug all that into your calculator, you should get 21,577.01. Take the square root, and you get a resultant force of 146.89 pounds. Number 9 and 10 deal with bearing. So let's take a look at those. Okay, so we've done a couple different types of bearings, but the ones that are really going to be important for our final exam are this type here, where it basically tells you what pole you're working with first. So it tells us that we're talking about the south pole, and then we're going to go west from that pole 28 degrees. And this distance that we're given is 350 miles. We want to know in component form, what they mean by that is AB. Basically, what's the size of the vector in the horizontal and vertical directions that represent this length here. So anyways, let's draw a picture and see what we come up with. So if we're going south, that means down. So our pole is going to start here and it's going to go down in the south direction. And then it's going to go west, which on a map would be left, 28 degrees. And it tells us the length of this line, or how far this ship has traveled, is 350 nautical miles. So here's the general picture. But before we can write it in component form, which is pretty easy, you have to think about this on an entire graph. So if I put in my x and y axis, not just this y axis or the south pole, kind of see what we're really working with here. We need to figure out first what this angle is. So I'll just call that theta. And then I'll show you some formulas for figuring out the components A and B. Pretty easy. So if this angle in here is 28 degrees, we know all the way to the south pole line would be 270 degrees. But I have to take that away. So 270 minus 28 gives us a theta measure, an angle measure of 242. Okay? So in order to figure out what A and B are, it's really simple. We take the magnitude or the size of the vector, which in this case is just 350 miles, times it by the cosine of the angle, but it's the angle from the positive x-axis, so be careful, do not put the 28 degrees in there, put 242 degrees in there. Comma, 350 sine of 242 degrees. Again, make sure your calculator is in degree mode if we're talking about a degree problem. If you plug both of those expressions in, you get negative 164.3 and negative 309.03. And this makes sense because if you think about this as just simply graphing a point and not a vector in component form, if we go negative in the x direction and negative in the y direction, that means that we're going, left and then down, which really just puts us in the third quadrant down here. Okay? So, and that's exactly where this vector is. So it makes sense. So take a second, see if you can do number 10 on your own before I show you my answer. Again, I'm going to start off by drawing the poles. This time we're talking about the a north pole, and we're still going west, so left 34 degrees. So our north pole is going to be going up. Then we're going to go west or to the left 34 degrees. And the length of this vector, or how far the ship's traveled, is 275 nautical miles. So 275 would be right here. So again, remember that we're talking about this on an entire, XY axis. So we're really interested in figuring out what this angle here, theta, is. So we know if we go up to the North Pole, or the y-axis, that's going to be 90. So we have to add an additional 34 to get theta, and we get 124 degrees. So now, just like before, I'm going to substitute in 275 cosine of 124 degrees. 275 again, sine of 124 degrees. And when we evaluate that on our calculator, we get negative 153.8 and 228.0 for our component form. So there's our two answers for numbers 9 and 10. And again, number 10 makes sense because we're saying go left and then go up, so on our graph, we go left and then up, we would be at the tip of that vector there.